Hello and welcome to today's webinar. My name is David Cash. I'm a member of the marketing team here at Mountz. I'm glad that you've taken the time to join us today as we look at our topic of how to calibrate your torque analyzers and torque sensors. Now, if you have any questions or any comments, feel free to put those in the chat. We'll have a question and answer time at the end of the presentation. So let's go ahead and jump right into today's presentation. So when we talk about calibration purposes for tools or for sensors, we might want to define what the calibration is. So calibration is typically we are measuring our tools with the use of a higher accuracy level of tool. So, for example, these are all part of any type of ISO specification or NIST standard or an international standard as well. And the calibration allows us for traceability through the process and also helps to gauge for any type of uncertainty that we might find as well. So all of this is encompassed in the actual calibration process, from the very beginning of the traceability to the final result of a tool, excuse me, or torque tool that is being calibrated. In this case, we're talking about torque sensors. So let's keep on going with that. Now, there are a number of different types of standards as it relates to calibration labs, and the actual calibration of whatever it is that you are using, whether it's going to be for a sensor or for a tool. But the typical ISO 9001, we are all probably pretty familiar with this, specification as it relates to calibration labs and for torque related products. That's going to be under the ISO 17025 regulation. And within that calibration process as well, we can also see the ANSI Z540 standard. And then there are also other international standards, the NVLAP, the British standard of the 7882, and also a German standard of the R38. So all of these will guide you or whoever is doing the calibration in what type of process we want to use for that calibration. In some cases, this may be the use of a 3-point calibration for the use of a torque analyzer, or maybe it might want to be a 5-point calibration. So it all depends on the standard that's going to be used. And we'll touch on that a little bit as we get through into our demo portion of today's presentation. But what calibration options are there for you as it relates to your calibration, or excuse me, your torque analyzers and torque sensors? Well, there's 3 of them, but primarily you can have your tools and your sensors sent out to a calibration facility where they do the calibration for you and then send the tools back. You could also have a mobile type of calibration service where they come to your facility and calibrate your tools in-house. And then lastly, it would be actually having the actual calibration equipment to be able to do that in-house with your own employees or your own staff doing the calibration. And there is some, obviously, some investment that is involved with that. There is training that needs to be involved with that. There are also procedures and other manuals that may need to be generated to make sure that the calibration, if you're doing it in-house, is followed to the standard which you would like, or in whatever the management would like as well. And so that's going to lead us to today's poll question. So we'll go ahead and launch that poll. It is a pretty simple question. How do you calibrate your torque analyzers and torque sensors? Do you use an outside service, or do you do that in-house? So I'll give you a quick minute here to go ahead and answer those questions. and we'll be back in just a second. All right. Thank you very much for participating in our poll. It is exactly split at 50% in-house and 50% use an outside vendor. So thanks again for participating in that poll. And so that will bring us to when we do our calibrations for our sensors or analyzers, what calibration intervals do we need? At Mountz, we recommend 6 months for you to begin at that rate. We do have customers that would like to see their intervals set to 12 months. And then we have some that will extend that out based off of whatever performance they might see from their analyzers. So if you start at 6 months and you see after the first initial calibration that you would like to extend that because the readings from that are well within specification, you can extend that to 12 months. And that could also go the other direction as well. So if you're using a 12-month calibration and you see some inconsistencies, you may want to move to a 6-month calibration on that equipment. And that could be because of the amount of use that that particular item is being used. It could also be for very critical type of torque applications where for a medical company or aerospace or anyone that may be reporting their results to the government or a government body, they may need to have that calibration interval done more often. So it just depends on, again, the amount of use, the specific tools that may be being used on that application. And it also could be the management goals and how they want to control uncertainty through the process of the calibration of the sensors and the analyzers. So as we take a look at the actual process of being able to calibrate the sensors in-house or just the general knowledge of how those sensors are calibrated, it's really good to know exactly how a torque reaction sensor works. And with that, we're going to be looking at resistance, and that is really the key to taking an analog input such as a torque wrench, putting that on a torque sensor, and then getting a digital value out of the analyzer. And the resistance is what we can measure from a strain gauge that is laminated onto a piece of stock. And this small little electrified circuit, as we apply torsion or a torsional load to the stock, this strain gauge, because it's laminated on the surface, will begin to move and bend. And through that process, it was going to change the amount of resistance that the circuit sees. And so the more torsion we get, we'll have one value versus no torsion at all, and another value that we would receive. And this is how we can take an analog, convert it to a digital signal, and be able to provide a torque value from that. So here's a little animation that highlights that. So we have our strain gauge that's laminated on our stock. And then so if there are torsional forces to that, it's going to change the actual geometry of the strain gauge. Again, changing the resistance readings, giving us that ability to change the analog signal to a digital signal. So here's an example of a gauge that was broken, but we went ahead and snapped a photo of that. So you can kind of see the actual part being used. So again, this circuit is electrified. This is what the analyzer is getting its information from and converting that into our torque value. So not only with the strain gauge that is part of it, but there are also additional equipment that needs to be purchased or used when we're doing a calibration in the actual portion of the analyzer. And so when we take a look at what torque equals, it's distance times force. So we use special designed segment arms and weights. These all are traceable to NIST. So all of the weights are Class F certified. And we have our wheels and segment arms, which provide our distance in the torque relationship. And then the weights provide, obviously, our force. And so, for example, if we were calibrating a 100 foot-pound torque transducer, if we have a 2-foot segment wheel and we want to provide 100% load to that sensor, we would put 50 pounds of force on the hanger, which would then be attached to the segment arm. And this is going to give us 100 foot-pounds of force multiplied by our distance, at 50 pounds times 2 equals 100. And this will be apparent when we look at the demo video that we have for you on that. So again, these items are calibrated as well. Another calibration step within the traceability chain from the absolute standard to the tool that is being used on the analyzer or sensor that we are using. So for very small torque analyzers, we would use a wheel, a very small wheel that could be 2 inches, it could be 1 inch, but those would be used for much smaller torque analyzers, and the Mountz capacity can go all the way up to 20,000 foot-pounds that we can calibrate in-house. So if we take a look at our demo that we have for you, this is basically a video of one of our technicians doing a 3-point calibration. Now, just to let you know, we do have 3 calibration labs, 2 in North America and then 1 outside of London in the UK. In America, we have 1 at our corporate office located in San Jose. Then we also have another one located at our distribution and warehouse facility in Foley, Alabama. So wherever you are, we can certainly do this type of a calibration service for you. But let's go ahead and jump into the video itself. So we want to first make sure that we have our sensor mounted to the correct bracket. Now in this case, we are calibrating our LTT 100F. So it has a built-in 100 foot-pound transducer. And so just like I had mentioned in when we were talking about the weights and hangers, we are using a 2-foot segment arm here with a total of 50 pounds of weights. So our hanger is 5 pounds. We have 2 plates that are 20 pounds and then 1 additional plate that is 5 pounds. So at first, we load the sensor to 100%. This allows the sensor to be exercised. So we let that hang for 30 seconds to a minute. I have cut the waiting time out of this video, so we can move the presentation along without unnecessary waiting. So once the exercise has been done, we will then begin the three-point calibration with the use of the software that is connected to the analyzer. So it is measuring the resistance and it is calculating what the amount of weight that is, and it's doing its calculations, and it is putting the calibration data. Once the entire process is finished, it loads that information onto our ARC2 chip that's within the sensor itself. So this will allow you to basically plug and play with other either a PTT or our LTT if we are adding an additional sensor. So we are now moving on to our 50% for our second reading within the calibration process. And another thing to keep in mind is that we want to make sure that the weight is very still while this process is going on, so there isn't any type of movement deflection that's happening that's causing any irregularities within the readings of the process. And so now that the 50% reading has been done, we'll now go ahead and we load back to 100%. And then this process is completed in the counterclockwise method, the same value or same readings at 10, 50, and 100. And then after that has been completed, the calibration data, as I mentioned, will go to the ARC2 chip where it will be stored there. And then the process will be validated to make sure that the sensor is reading correctly with that. And then at that point, the calibration has been completed. So the process itself is not too terribly difficult. There is just a number of things that need to be managed within the process. Obviously, this is done in our calibration lab where we have the temperature is controlled, the humidity level is controlled, and then we're also they're controlling the specific gravity as well. So that can play a part in our calibration process as well. So with that, that's going to kind of lead us to our questions and answers at this point. So let's go ahead and jump to that. So Chris, do we have any questions?
Morning, Dave. One of the questions that came in was, with that arm, does the length impact the testing or the calibration process?
So the arm is going to allow us to get to certain steps within the actual loading process. So in this case, in the demo video there, we were using a 2-foot arm with 50 pounds of weight to get us to our different points at 10, which would be a 5-pound weight, at 50%, 25 pounds, because our distance times force. So if we change the lever arm, then we're going to need to change the amount of weight that we are adding to the hanger or a wheel. Just depends on the actual torque that's being generated. But if we were to use a 1-foot wheel, or excuse me, a 1-foot segment arm, then we would need a full 100 pounds to be able to get to 100 foot-pounds of torque. And then if we extended that arm to a 5-foot segment, then we would be using much less weight, obviously, than we would be in either the 2-foot or the 1-foot section. So the arm itself just determines the multiples that we may need for a known weight to give us to our certain points of value that we may need.
All right, Dave, thanks. Another question we had was, before the calibration process starts, is there like a warm-up you have to do with the torque tester or some type of process?
So typically, you're going to want to exercise, again, the sensor for at least a minute or so at 100% of the rated value for that tool. And then you can also have that within the lab for 1 to 2 days before to make sure that there aren't any changes to any of the other componentry and that there is a complete equilibrium at the with all of the components.
All right, Dave, that looks like that was all the questions we had for today.
All right. I want to say thanks for joining us today. If you have any questions further, or you'd like some information regarding the Mountz calibration services or calibration equipment to bring in-house to do it yourselves, feel free to reach out to us at our website at mountz.com. We appreciate you joining us today, and we look forward to seeing you again next month. All right. Thank you so much, and have a great day.